let's move on. So once we understood how to stabilize basic systems, either through essentially through reverse engineering of Lyapunov functions, this is a nice example where a particular class has a generic framework to design the controller, but in general it's not that easy. Unless it's dissipative or something like that, then we can use the dissipativity ideas, right? Then we actually moved on to basically an extended discussion of optimization, functional optimization, and then finite horizon optimal control, and then finally infinite horizon nonlinear feedback control, which essentially is stated something like this. If you have a system x dot equals f of x comma u, where you use the input, of course, and we want to minimize, see this cost function j, which is in terms of the integral of L of x comma u. So typically this is a quadratic function perhaps, and then non-negative in x and quadratic in u and things like that, right? So the designer's job is to basically essentially find feedback stabilizing controller that minimizes this cost over all stabilizing controls, right? So the solution theory is quite interesting and unique in the sense that you don't necessarily remember how to do it. We don't have to, but the solution is fairly straightforward to understand and also remember if you want to. So the first part says if you have a function v and phi, feedback control loss, such that the closed loop system is stable. So from the straightforward application of Lyapunov theorem, the first two conditions will come. The optimality comes from the fact that basically if you add L1 to your L substituted phi with into that L plus this Hamiltonian part is going to be 0, where p is picked to be v prime, and also this same Hamiltonian with u being a some other value other than phi of x, and if that happens to be greater than or equal to 0 for all u, then we have optimality, right? So we phi of x is going to be optimal control. It's quite like I said, required a little bit of work to actually reach this particular part, but otherwise application is something that's quite I won't say simple, but not so difficult, right? So I'm going to consider this system. So minus x cube. So x1 dot is equal to minus x1 cube plus, if I'm not mistaken, something like this, and x2 dot is equal to minus, I believe that's correct, okay? And the cost function is basically 2x1 square plus 2x2 square plus half u square. So it's a cost that minimizes both the state and control in a quadratic fashion, and of course the weighting of 2 and 2 and half and things like that tells you something about which is more priority for us and things like that. So we have to define h of x comma p comma u, or it's the other way, as L of x comma u plus p transpose f. So that's nothing but 2x1 square plus 2x2 square plus half u square plus p transpose f is minus x1 cube plus x12. Yeah. So if you actually take p to be a constant here, and you will end up with a linear function in quadratic part in u and the linear part in u. So let's say p is p1 p2. You'll get p2 x1 square u plus some complicated function involving x, right? And we know by actually minimizing this, right? How do we minimize? Set this hu is equal to 0, and that will tell me u is going to be equal to minus 2 times p2, sorry, not 2, just minus p2 times x1 square, right? And substitute in this particular equation, you'll get a huge equation in p1 and p2 and x1 and things like that, okay? So I'll get something like 2(1) square plus 2x2 square plus half p2 square x1 power 4 plus p1 times x1 cube minus plus x1 x2 square plus p2 times minus x2 plus x1 square u is minus p2 times x1 square, and it's not surprising that you'll have x1 power 4 here, right? And we will, we are supposed to basically this is the equation in P and the optimal x, and then we are supposed to basically substitute for v prime and hope that this entire thing is going to be 0, right? And and if we are lucky enough, basically we can try something like v equals half x1 square plus alpha over 2 x2 square or something like that, and maybe alpha plus beta over 2 x2 square, and if it works out, well and good. Otherwise we are typically in trouble in terms of basically trying to find a simple method to solve this, but essentially we have to solve that particular equation. Once we solve that equation, that gives you v prime, and then that gives you therefore p2 and all those things, so you'll get the feedback controller that stabilizes and minimizes the cost that we have, right? So I will leave some of these details for you to explore, but I want to go back and talk about the finite horizon control. Suppose if I had j is equal to this, the same function 2x1 square and some things like that. Well, it's much more difficult than this one. It's not going to end up with something like this, but if you recall, basically we will get equations like x dot equals partial h with respect to p, and p dot, you will actually have an equation corresponding to your p part. P dot is equal to minus partial h with respect to x, and then also we need to satisfy partial h with respect to u is equal to 0. And this is an initial value problem, the standard differential equation that we are trying to solve. And of course, this p dot is actually going to come from the fact that you have some kind of final condition, and this will typically give you a function for u in terms of p's and things like that. So, and then this becomes a what we called as shooting value problem, in the sense that we have one initial value problem and the other one is a final value problem, and there is no simple way of solving this except in discrete time. So therefore we keep shooting from initial value problem for some p, and then hope that it will catch the final value, and then somewhere there's some kind of binary search algorithm goes on, and then hopefully we'll find some kind sorry, not binary, bijection kind of method works, and then eventually hopefully we end up with an answer there, right? And though I didn't show you rigorously and things like that, one can actually try to show that p dot is going to become 0 and things like that, and then these things eventually will boil down to the same equations that we get in the infinite horizon. Okay, so so that was optimal control with feedback, right? And what about the next topic that we chose? One of the topics that we actually did ahead of optimal control was this cute idea of adaptive control. Again, it is about controlling systems for a general class, but here the typical assumption is basically if we don't know exactly something about this particular system, the standard assumptions are some parameters unknown and things like that. And there are multiple ways of addressing this particular problem. Let's say if you are not even interested in control, then it is a matter of parameter identification. That is one problem. The second one is, once we know how to identify the parameters, perhaps use that knowledge in the feedback, and then use the parameter estimate as the proxy for your actual value of the parameter, and then treat it as a standard feedback control problem. And combining these two ideas is actually much simpler approach, what people call as directive adaptive control, which essentially says that, okay, fine, I don't know these parameters, but I know that there is some parameterized form of equation that stabilizes this particular system. So in other words, I have a u, and then there is some k1, k2, k3 such that when I put u equals k1 times h1 plus k2 times h2 and so on and so forth, that stabilizes the system. It's just that I don't know what the values are, k1 and k2 and things like that. In that particular case, so how can we solve this particular problem, right? So then the entire idea of adaptive control is basically, no, I'm not going to assume that I know these values of k1. Instead, I'm going to estimate the value of k1. So this is a very important difference, subtle difference, but important difference. I mean, once you understand, it's a fairly straightforward difference. In the indirect adaptive control, we estimate the unknown parameter and then try to use that estimate in the feedback control. Whereas in the direct adaptive control, I don't care about the parameter anymore or estimating the parameter so much. I just want to estimate the controller, and then that's a far simpler way of approaching any problem in general. What you want to estimate versus what you want to do is a big question. So this actually simplifies a lot of the mathematics as well as implementation, right? So anyway, through our Lyapunov function approach, we actually can come up with the what you call the update law for the estimate, right? There is a method to this madness in terms of how one can estimate the parameters of k1, and then eventually what we can show is unfortunately is not a straightforward application of LaSalle. It actually goes slightly deeper into the time varying theory for such systems, and then basically the mathematics is slightly more complicated than the standard Lyapunov theory, but the idea is the same. We will use this V and then show that eventually this particular system is such that x goes to 0 and k hat goes to some constant but not exact value of k1, right? So as an application of this, basically if I had a polynomial system, obviously I know that I can cancel out all the nonlinearities to this polynomial. The good thing about this is basically, suppose if a1 happens to be negative or a3 happens to be negative, then perhaps we don't have to cancel that particular part, and then adaptive control law that we are developing may be smart enough that this k1 and k3 will remain 0 or something like that, right? So otherwise it's a straightforward application of that, and we'll see. I mean that works in that sense, right? And then this idea can be extended in multiple different ways. So if you had a second order system that mimics your standard, let's say what you call spring mass damper system or the nonlinear version of it, and what can we do with it? Well, here I made a very special assumptions. Beta is still very nice function. Beta of x times x is positive, whereas I don't know anything about alpha except it's lower bounded. So different conditions, right? So that's the problem statement. And how can I do this? Well, if I knew exactly the lower bound for this alpha, I can basically cancel out this particular quantity through standard linear feedback control for this u, right? But typically, if I don't know what is the lower bound could be 10, it could be -1, it -10 and things like that. Since I don't know that, then what can I do? Well, again, the same idea. We use adaptive ideas basically by saying that I know it exists, I'm going to estimate that, and then the estimator is basically designed through our Lyapunov function, and the Lyapunov function has to be chosen appropriately. I mean, the same idea is going to repeat. Basically, somehow we have to translate it to some parameter estimation problem where the parameter estimate, in this particular case in direct adaptive control, the parameter corresponds to the feedback controller, and that can be essentially estimated through feedback law by using the appropriate Lyapunov function. And then really no standard method beyond the few examples that we see, and you can generalize it a little bit more. That looks very confusing, but essentially the idea is the same, right? So the same idea can be extended. Instead, if I want to say not just stabilize but actually track some other stable system. The basic system need not be stable, but the feedback control, we should be able to stabilize it, but then once we stabilize it, it should be able to track some system, right? And this we called as model reference adaptive control, and the idea is same. So I'm not going to repeat much of this. We have gone through this extensively at some point, but I want to go back and show you slightly new problem and then see what happens, and then how we succeed in certain cases and how we do not, right? So hopefully you will see one last example, the adaptive control idea. And suppose I had something like this, x square plus x hat, and then u is equal to a x hat dot is equal to I don't know, a x hat plus u. Okay, so this looks very much like the cascade system I want. I was talking about. So this x hat could be viewed as a stabilizing controller for the first one, and the second one has its own dynamics, and then we want to cancel the second one. But then if we stabilize the first one, then if we stabilize the second one through u, hopefully the first one gets stabilized because x kind of going to 0 and things like that. Except I'm going to assume a is unknown, right? So can I actually use my adaptive ideas to solve this particular problem? So if you recall, basically, let's treat each one problem. So this particular problem, I could realize that by doing this, something like minus x square. So this minus x square, when I put that in place of x hat, that stabilizes. So that's like basically adding and subtracting this. Okay, whereas this part somehow we'll figure out what needs to be done. And for the time being, let's assume that we know this exactly this thing. So I could choose u to be minus ax hat plus question mark, right? So if you recall, basically the procedure is something like I can choose half x square, okay, plus half x hat plus x square whole square, right? And if I basically try to compute the derivatives, I'm going to get something like x hat dot plus x dot plus 2x dot, which I know what it is, and x dot on the other hand is ax plus bu. So ax hat plus u. So ax hat plus u, and so u can be picked in such a way that that becomes minus of some small number multiplied by that, right? So this was the idea that we used for cascade systems. This is how we actually solved. Now the problem is here we don't know a, right? So what can I do? Well, I can actually instead of doing this minus ax hat plus all this junk, right? C times x hat plus x square plus all this x dot kind of a thing. Instead of that, I'm going to basically assume a hat, right? And to this, basically, I'm going to add a hat minus a whole square, where I'm going to design a hat dot is equal to question, right? One of the things we need to understand is when we try to do all those things, eventually nowhere you should depend on the unknown parameter a, right? Similarly, a hat dot also should not depend on the unknown parameter a. Okay, so in fact, so this is how one can apply or extend the idea of a feedback system in this cascade framework. But let's try to extend this idea to something else, right? So suppose, let's say x dot equals ax plus x hat, and x hat is equal to, I don't know, for the timing we don't even care about that, right? So let's suppose this is simply u. So in this particular case, we'll assume a is unknown. If it were known, then we could actually solve this entire system as v is equal to half x square plus x hat minus some k of x, where k is such that k plus a is less than 0, right? So that's the feedback stabilizing controller if you view x hat as the feedback, and this cascade idea we are trying it, right? But if we don't know a, then we don't know k, and then how do we deal with it? Well, I could try this, right? Instead of that, basically half of x square plus half x hat minus k hat of x, okay, plus half k hat minus k whole square. Let's see what happens, right? I mean, this is getting slowly complicated, but hopefully. So I'm going to get xx dot plus x hat minus k hat x times x hat dot, right, minus k hat dot x minus k hat x dot, okay, plus k hat minus k times k hat dot. Okay, so as you can see, you have this k hat dots, which needs to be determined, and then this k hat minus k is unknown, so we have to be careful about that particular part. And I can basically substitute. So I have x dot times, sorry, let's see. Okay, so x dot is ax plus x hat, okay, plus all this thing, okay. So I'll get a plus k x square, which is nice, it's negative, plus I'll get something like k x hat minus k times x, right? So the thing is, as you can see, basically this part has x minus kx, whereas this part has x minus k hat. So we can add and subtract that, and hopefully we can pick our u and things like that, but it's getting complicated. My suspicion is it won't work out, and then that's the difficulty. One can try out some of these ideas, but then we will eventually end up with basically we'll have u equals something, k hat is equal to something, right? Either of them may contain k, and then that will essentially ruin the procedure, right? Because the idea of adaptive control is basically we want to solve this particular problem without using the knowledge of certain parameters. If we don't know a, at least we know that there is some k which is still unknown that stabilizes this, and then using that idea and then this cascade idea, we can try to construct this, but we'll end up with a real mess. And then I would urge you to basically try and convince yourself whether this works out or not. I mean, it's an open problem for you to consider. It's kind of a research problem, per se, right? So that essentially brings us to the end of lecture 12, last but one lecture, so to speak. And the key ideas, therefore, in terms of wanting to remember for the longest time is, of course, the basic idea of stability, and then how to find stability for how to check stability using these Lyapunov functions, right? That's the first idea. The second idea is this extension to input-output systems, this concept of dissipativity, which was very useful in specializing to robust stability analysis and absolute stability problem. So that's the analysis part. Then of course we looked at feedback control systems. One of the first ideas is basically the feedback dissipative systems. If you have two systems in feedback with certain supply rates, they stabilize with each other. So that's one idea that's very, very important for us to remember, and that obviously is very useful to do a lot of things in robust control. But beyond that, in general, we'll have a class of feedback controllers which we can optimize against and things like that. So that brings down to, of course, optimal control, and it's complicated enough that we can worry about the stability, but then optimality is even one more layer on top of it. And then we have some sufficient conditions that are applicable to some very special classes of systems, but otherwise it's general theory, right? But whereas the finite horizon problems, where we don't really worry about stability, we can actually do something interesting there, and then and that's how one can people solve these what do you call finite horizon problems, like sending a space shuttle or many things like that. Others are more academic, but the most applicable that I can think of in optimal control is actually sending space shuttles from one point to another, where the disturbances are practically not there, and then you can actually set a path and then follow that, right? So these are the various key ideas, and of course we also looked at disturbance rejection and then how to combine all these things. Individually we understand each one of these ideas. In reality, we have to be able to combine all these ideas and then solve the problems. Adaptive control is one such idea. The cascade systems that I showed you is one such idea. And of course, the difficulty of solving these problems is going to be there inherently. You have these ideas of linearization or using semi-definite programming for polynomial systems. In a way, that's good, because the polynomial systems, at least instead of approximating something with linear and throw away everything nonlinear, we can approximate it with nonlinear and retain some nonlinearity, and then that gives us a bigger domain of attraction. Then use semi-definite programming and sum of squares ideas to solve that particular problem. So that's in a nutshell the summary of what we tried to do in this entire class. Is very subtle and complicated from a mathematical perspective. From an application perspective, it is relatively straightforward to understand why we are doing these things. Solving problems, it's somewhere in the middle. It's not, it becomes an art to solve each and every specific problem. Hopefully you have seen enough problems to get that practice and then attempt to solve some newer problems, right? So that will bring to the end of our lectures, and then last lecture is simply some generic ideas that we haven't really paid attention to, and we will look at that in the next lecture. Thank you.